The heliocentric model functioned as an engineering solution to mechanical failures in ancient astronomy. Looking past this single discovery reveals the diagnostic method. For over 40 years, Copernicus served as a hands-on physician in Royal Prussia, diagnosing complex regional epidemics and personally compounding botanical pharmaceuticals to treat physiological failures. Linguistic analysis of his Latin translations reveals a deliberate stylistic shift away from medieval scholasticism. He sought out the rigorous, cross-disciplinary methodology of Renaissance humanism. As an ecclesiastical administrator, he commanded besieged cities during the Polish-Teutonic War and engineered logistical solutions to devastating macroeconomic crises. Placing the sun at the center of the universe was the final output of a systems-level diagnostic methodology applied to the heavens. Copernicus processed reality through structural axioms, applying this diagnostic logic to inflation, as he did to orbital mechanics. Following the Polish-Teutonic War, the region of Royal Prussia faced severe economic destabilization, requiring Copernicus to manage local logistics in a failing system. The primary vector of this crisis was monetary. The Teutonic Order was covertly debasing their minted currency. They replaced the precious silver content with cheap copper alloys, while legally demanding that the coins maintain their original face value. This flowchart maps Copernicus's observation of rational market behavior. When a government enforces a fixed exchange rate between currencies of different intrinsic purities, people immediately hoard or export the high-purity silver. They exclusively use the debased copper to pay domestic debts and taxes. This behavior defrauded buyers and sellers. By identifying this, Copernicus formalized what we now call Gresham's law. Bad money inevitably drives good money entirely out of circulation. This graphic highlights his 1526 treatise on the minting of coin, where he abstracted this physical crisis into a macroeconomic law. Here, he formulated the earliest explicit version of the quantity theory of money. He hypothesized a direct linear causal chain between the total money supply and the general price level of commodities, predating the modern equation of exchange by centuries. He also recognized that monetary expansion operates gradually, secretly eroding the wealth of whoever is last in line to receive the new inflated currency, a primordial definition of the Cantillon effect. Copernicus possessed a unique capability to take an isolated, confusing data point, like the rising price of bread in a local market, and abstract it into a mathematically holistic framework. He applied this exact intolerance for systemic fraud to the architecture of the prevailing Ptolemaic universe. Ptolemy's geocentric model was computationally successful. It accurately predicted the apparent backward loops of the planets, but it relied on a flawed geometric device to do so. This diagram visualizes the problem. Aristotelian physics dictated a strict constraint. Celestial bodies, composed of immutable ether, must move in perfect, uniform circular motion. To force his model to match observational data, Ptolemy introduced the equant. This was an artificial, off-center point in space. From the perspective of the equant, the center of a planet's epicycle appeared to sweep through equal angles in equal times. But because the equant was physically off-center, the actual planet had to repeatedly accelerate and decelerate as it moved along its orbit to maintain that constant angular rate. For Copernicus, the equant sacrificed physical reality for computational convenience. It was a mechanical aberration that violated the laws of physics. The mandate to abolish the equant drove the shift to heliocentrism. Copernicus prioritized the restoration of uniform circular motion over the central position of the Earth. In an early manuscript circulated prior to 1514, known as the Commentariolus, Copernicus realized the equant could only be eliminated if the Earth itself were put into motion. Looking at the text of his initial postulates, the third and fifth rules explicitly shift the center of the universe near the Sun and assign a daily diurnal rotation to the Earth. The seventh postulate details the mechanical solution. Earth's orbital speed organically accounts for the retrograde motion of other planets. It is purely a parallax optical illusion caused by the faster-moving Earth overtaking the slower outer planets. It took 3 decades of empirical data collection to formalize this geometry into his 1543 magnum opus, De Revolutionibus. But modeling this new architecture without using the equant required immense mathematical complexity. Ptolemy's lunar model used a crank mechanism that mathematically forced the moon to appear drastically closer and over 4 times larger at certain points in its orbit, a physical impossibility entirely refuted by visual observation. Copernicus solved it with a double epicycle model, visualized here. He stacked constant-rate circles to achieve a variable velocity. This vector addition matched the moon's actual orbital speed without drastically altering the Earth-Moon distance, preserving perfect circular motion at every joint. To model planetary longitude, he also utilized the 2C couple, a mechanism that generates linear harmonic motion purely from the combination of 2 uniform circular motions. These exact mathematical linkages were engineered centuries earlier by Islamic astronomers associated with the Maraga Observatory in Persia and the Umayyad Mosque in Damascus. Historians remain divided on how he acquired them. Some point to an unrecorded channel of manuscript transmission from Damascus to Italy. Others argue that highly skilled geometricians operating under the exact same Aristotelian constraints will independently derive the exact same mathematical solutions. Regardless of their origin, Copernicus inverted these tools. He repurposed mechanisms meant to perfect geocentrism to prove a heliocentric universe instead. Rigorous empirical physics drove the 17th century resistance to heliocentrism. Astronomers relied on specific mechanical and optical arguments that the moving Earth model could not yet answer. In 1651, the Jesuit astronomer Giovanni Battista Riccioli published an encyclopedic compilation cataloging 77 highly sophisticated scientific arguments against a moving Earth. Riccioli's first major critique anticipated what we now call the Coriolis effect, testing orbital mechanics with heavy 17th century artillery. The logic was sound. If the Earth rotates, ground at different latitudes moves at different speeds. A projectile fired north should exhibit a measurable deflection. But 17th century ballistics lacked the range to measure this. Finding zero deflection, empirical astronomers logically concluded the Earth was stationary. Riccioli's second critique relied on the telescopic star size argument, a geometric problem stemming from the lack of observable stellar parallax in the night sky. Early telescopes produced false disks of light around stars due to diffraction. Mistaking these for actual physical bodies, Riccioli applied basic trigonometry. To satisfy the Copernican model, every single star would need to be vastly larger than our entire solar system. Based strictly on the optics and mechanics known in the 1600s, heliocentrism violated all known principles of physical proportionality. It was rightfully rejected by the era's most rigorous, data-driven astronomers. It took centuries of further advancement, Newtonian mechanics for rotating reference frames, and wave optics for telescopic diffraction, to fully vindicate the Copernican model. Copernicus operated as a physician, economist, and humanist, identifying structural inconsistencies across every system he managed. By demanding mathematical and physical integrity, Copernicus established a diagnostic standard that exceeded the observational limits of the 16th century.